Chapter 9 in our textbook, and it has to deal with what I would assume for a lot of people is probably the most frustrating thing about weather, and that's that it's not that easy to predict. It's not that easy for us to actually be able to look into the future and really figure out what's going on. And I'm sure you, like me, have had days that have been ruined by a blown forecast, whether it was something like a picnic you had planned got canceled because of rain, and then it didn't rain, or you were out on your bike or something, and all of a sudden a big storm comes and you have to run for safety. And a lot of this comes from the fact that really weather forecasting is very difficult to do. Now, for most of us, a blown forecast simply just means something like a ruined day. It's a big deal to us, but it's not really the biggest deal in the world. However, for many people, a blown forecast can actually cost millions of dollars. With that said, this week we're going to talk a little bit about the science behind weather forecasting. So, the first thing we're going to do is we're going to talk about some of the key components of making a weather forecast and some of the key steps that are involved in developing a weather forecast. So, we'll talk about some of the things that go into it. We'll talk about some of the methods used. We'll talk about some of the tools available. And so let's jump in. So as I just said, weather forecasting is essentially predicting the future. So if you think about a fortune teller who looks into a crystal ball and looks for that crystal ball to tell them what may be happening in the future, meteorologists essentially are doing that. They're looking into a crystal ball to determine the future. However, what is in that crystal ball? Well, there are two key things that go into making a weather forecast. The first thing, similar to what a doctor would do if they wanted to figure out what the current situation of somebody is they would make a diagnosis. They would gather data, they would run tests, they would analyze things, and then come out the other end with a diagnosis, basically saying, okay, this is what's going on. And then based on what they know, based on the trends that they've seen, based on how they've seen things develop, they can then make what's called a prognosis. And that prognosis is the prediction. So the diagnosis represents the current condition, the current state of things, and then the prognosis represents where things are headed. So let's talk about this. So first and foremost, in order for us to actually make a weather forecast, we need to accurately acquire weather data. And thankfully, this isn't much of a problem for us. Right now, as we speak, as you are listening to this video, there are weather stations scattered all across the world that are collecting all the weather data that we need to know, collecting temperature data, dew point, wind speed, wind direction, precipitation. You also have people launching weather balloons into the atmosphere, getting readings of weather conditions in the upper atmosphere. And then even for locations that don't have a weather station, there are satellites flying over us right now that are actually gaining large-scale observations of weather systems and weather conditions. So they're looking at things like cloud patterns, which can then indicate the presence of an organized storm system. You also have Doppler radar scanning around looking for the location and the movement of precipitation. So all told, there's lots of weather data currently being collected. And as a result, all of this weather data then needs to be processed, it needs to be analyzed, it needs to be looked at, and it needs to be readily available for meteorologists to make their predictions. There's a few ways that we can do this, and thankfully there's a lot of tools that do this for us. There's a lot of clearinghouses that we can go to gather weather data. Here in the United States, the quickest place you could go to gather weather data would be the National Weather Service. If you ever want to visit the National Weather Service, go to www.weather.gov, enter in your zip code in the upper left-hand menu, and it'll give you current conditions as well as conditions for the last 7 days, as well as a full forecast for the next several days. With that said, the National Weather Service is primarily an operational meteorology organization. They're mainly focused on making short-term forecasts. Now, they do have long-term forecasts as well, but they're only looking at data in the short term. That data, after it's done with the National Weather Service, is then archived somewhere where it can then be accessed. And a few places you can do that. The World Meteorological Organization, the WMO, they're not just the global governing body of meteorologists, they also represent weather data and meteorology across the entire world. And then finally, that clearinghouse I talked about can be found at MesoWest. And if you're in my online class, you've already seen MesoWest a few times this quarter. And it's incredible that you can actually go to MesoWest and access data from years ago. Access weather data from years ago. And so you can watch how local weather patterns have changed over a long period of time. Now, once you access that weather data, you want to be able to conveniently view it. And there's actually a few tools available to meteorologists for meteorologists to do this. The first one is called the Advanced Weather Interactive Processing System, or AWIPS. And what this does is this is basically a workstation that meteorologists have available to them that then allows them to process and to also visualize data. So all of those colorful weather maps that you see on your screen right now, such as this weather map here, this one right here in the middle, this actually shows water vapor and dry areas. This map over here is showing air temperature. This weather map over here is showing upper air patterns. Well, you can actually have that data immediately visualized and plotted on weather maps for you through the AWIP system. And so rather than having to draw the maps yourself, rather than having to sit down and look at the raw figures, you can actually instead have it all analyzed and processed for you so you can then utilize it in making your forecast. So AWIPS is just one tool. Another valuable tool that I like to use is what's called a meteogram. So what meteograms do is they take all the weather conditions for a given location. If you look back at AWIPS, this is actually for a large range of locations. So here you see much of the eastern United States, similar region here. For a meteogram, you're just looking at one location, and you're specifically looking at how weather conditions have varied over that location over the last 24 hours. So let's talk about each one of these panels that indicates different weather conditions taken at this location. So first off, this location is KSJC. If you don't know, SJC is the airport code for San Jose Airport. And so this is the San Jose Airport. And what this shows is the variation in weather conditions over the past 24 hours. And here's what you see. So this top panel shows air temperature and dew point temperature. So this top line right here is air temperature. And it shows you that how air temperature has varied over the last 24 hours. And you see an obvious, what I call diurnal pattern, where air temperature goes up during the daytime, down at night, and then back up during the daytime. The other temperature that you see here, as I just mentioned, is dew point temperature. You don't notice nearly the same kind of pattern for it. There's very little variation for it. This second panel is actually showing us three key things that we need to know. This top little area up here is showing any kind of precipitation that happened. The second panel is showing visibility. And then this third little area here is showing cloud cover, wind speed, and wind direction. And these are basically drawn using the same station model that we looked at all the way back in Module 1. The shading of the circle indicates cloud cover. The long pole sticking out of the circle is what we call a wind barb that indicates where the wind is coming from. And then the little feather at the end, or the number of feathers, indicates what the wind speed is. So if you want to learn more, if you want to review that, going back to Module 1 and going back to the station model for Module 1 would be really helpful. The third panel down here, this panel actually represents cloud cover. And it shows you two things. One, it shows you if the cloud cover was scattered or if it was completely overcast. It's scattered if you see dashed lines, it's overcast if you see a solid long line. And it shows you how high up in the atmosphere those clouds were present at. So if you take a look, we have scattered clouds at approximately 1,000 feet and then overcast a little bit higher. And then it varies throughout the day. I won't go into details on that, but that's just what this is showing you. And then this last thing that we're looking at down here is the air pressure in millibars. As I've said in the past, we mainly look at air pressure in millibars. And this particular graph is showing how air pressure has changed over the last 24 hours. And if you take a look, we've seen a variation of a little less than 4 millibars in air pressure, and that's actually pretty common. Unless a storm system is moving through, you're not going to get any major 10, 20 millibar change in air pressure. You're just going to see 2, 3, 4 millibars overall. So this is a meteogram. This is another thing that meteorologists can use to identify pretty quickly how weather conditions have varied at a location over the past 24 hours. The last thing that we look at are what are called soundings. And you've actually done a few of these so far this quarter. These are plotted on what's called a Stuve diagram. And the Stuve diagram shows a few different things. What I want you to look at primarily is these two black lines. The black line to the right represents air temperature. The black line to the left represents dew point temperature. And what you notice is whenever the lines are very close to each other or on top of each other, that represents saturated air. Wherever they're far apart from each other, that represents unsaturated air. Meanwhile, over here you can also look at how wind direction and wind speed changes with height. This can actually give us really good tips of what kind of advection there might be. There's a type of wind called a backing wind, where the wind is rotating clockwise, and that's indicating a type of air advection. Or there's another type of wind called veering, where these wind barbs are rotating counterclockwise as you go up in height. And so we look at that. We can also determine the stability of the atmosphere looking at this. So there's a lot that we can determine looking at these upper air soundings. And again, that all goes into making a forecast. Now, once we have all of that data collected and once we have a really good idea of what the current weather conditions are suggesting, we then take all of that data and we plug it into a computerized set of equations called a forecast model. And this forecast model uses these equations, they're called prognostic equations, to then create a weather forecast. Now the way that this works is the computer model isn't just using one equation. No, there are actually equations for different variables we're looking at. So there's a prognostic equation for temperature, there's one for humidity, there's one for cloud cover, there's one for wind speed, and so there are all these different locations. And when the forecast model is making the forecast, it's only making it for one location. That wouldn't be that useful. So instead, what we as meteorologists do, or what these forecast models do, is rather than running the equation just for one location, they actually take our Earth up and they split it up into a grid series. So imagine a map of the Earth and then splitting it up into, say, 4 equal squares. And then you do a forecast for each one of those 4 squares. And we don't just do this for the surface, we also do it for different layers of the atmosphere. And we'll talk about that in a second. The problem with forecasting, or the problem with forecast models, is a forecast model is like any model. In order for it to work and in order for it to be efficient, it has to be simplified. So we have to remove some complexities from the atmosphere. And as a result, the forecast model does not perfectly represent the atmosphere that it's modeling. It doesn't perfectly represent it. Instead, unfortunately, the forecast model only gives us a basic representation. With that said, these representations are still pretty good. They still get the job done very well. So if you think about comparing a large Boeing 747 airplane to a model version, the model version may still be able to fly. So it does the main thing that the big one does. But you may not have the same control over it, you may not have the same features of it, because it's a scaled down representation. Well, the same is true of forecasting models. So as I just mentioned, a forecasting model takes the surface of the Earth and it splits it up into a grid system. And then it runs those equations, it makes a forecast for each square in the grid system. Now there's a problem with this. The problem with this is that even if we take a look at this grid system right here, the problem is that a lot could be happening in just one grid box. Imagine a model such as imagine a forecast model for the Bay Area. And let's assume that it only splits the Bay Area up into 4 different squares, 4 different grid boxes. And let's assume that the grid box for San Jose also covers Santa Cruz. Well, the forecast for San Jose and the forecast for Santa Cruz should be very different. But that grid box would only make the forecast, would only give us one forecast for both locations. That's what we call a low resolution forecast. And so there's a problem with that. And I'll actually show a little bit more about that in a moment. So here's how these forecast models work. So you take the current conditions, those initial current weather conditions that we collected, you throw them into the model, and then the model makes a forecast. And usually it makes it for a short timeout, so it makes it for 5 minutes from now. Then the results that come out of the forecast model are then fed back into it, and a forecast is made for the next 5 minutes. Then the results from that are then fed back in, and then for the next 5 minutes. And then fed back in for the next 5 minutes. And so on until we have a long-term forecast. And so this is how we make a forecast. Now the good news is making a forecast for 5 minutes out is probably going to be pretty accurate. Even 10 minutes out, 15 minutes out, 20 minutes out. However, the longer out you go, the less accurate the forecast is going to be. You're going to have some kind of error, and then that error is then going to be fed back into the model, and so it's going to become greater. That's one of the reasons why, if you've ever wondered why we don't necessarily trust forecasts 7 to 10 days out, or why we can't have a forecast for like 3 months from now. It's actually because the further out we go, the more error we get in our forecast. And so eventually, the further out you go in time, the less accurate the forecast is. And so a forecast of 3 days from now is probably going to be pretty good. 5 days from now is probably going to be pretty good. 10 days from now, maybe. 15 days from now, no. Anything longer than that, absolutely not. So if you ever go on AccuWeather and see their 45-day forecast, you can get a forecast for way out from now. Don't believe it. A lot will change between now and then. So I just mentioned a minute ago about those grid boxes. And the Earth splits, or these models split the Earth up into a certain number of grid boxes and then do a forecast for each one. Now, the larger the number of grid boxes, the more accurate the forecast will be. So as I mentioned a few moments ago, imagine if you have one grid box that covers all of San Jose and Santa Cruz. The weather conditions between San Jose and Santa Cruz are very different. San Jose is much further inland, Santa Cruz is right on the ocean, there's a big mountain range between the two cities. There could be a lot of variation between the two. And yet that grid box would only make a forecast, would only give us one forecast for everywhere in that grid box. That's not good enough. If instead we took that same grid box and we split it up into 16 grid boxes or 64 grid boxes, we split it up into a lot smaller boxes. Now we have a grid box for San Jose, now we have one for Cupertino, now we have one for Sunnyvale, now we have one for the summit of the Santa Cruz Mountains, now we have one for Sanborn County Park, now we have one for Santa Cruz. We all get our own grid box, and therefore we all get our own forecast. The forecast would be much more accurate. The problem, however, is the more grid boxes you have, the more times this model has to make a forecast. And so the longer it takes, or the more work is needed, the longer it'll take. And this is actually a problem that meteorologists have, because the more accurate our forecasts become, or the higher the resolution of the forecast, so splitting the Earth up into millions of tiny grid boxes, it takes a long time for the forecast to be created. However, if we had a low resolution forecast, so the entire South Bay as just one grid box, that's great. But it wouldn't be as accurate. Again, the weather conditions in San Jose are very different than the ones in Santa Cruz. You can't really represent both locations in one forecast. A good analogy to this would be, suppose you have a picture of Mona Lisa. And on one side, the picture of Mona Lisa is basically just a bunch of grid boxes with colors in them. And let's say you have a small number of grid boxes. So you have a lower resolution. You can kind of still pick out her face. You can kind of still see, I can still see her eyes. I can still see her nose. I can still see her hair. But you really don't get a good representation of Mona Lisa. On the other hand, a higher resolution image of Mona Lisa is going to give you all those nitty-gritty details. But now, instead of having a relatively small number of grid boxes, you now have many, many, many more grid boxes. And therefore, each grid box has to be assigned a color, each grid box has to be processed, each grid box has to go through. So it takes longer. There's much more data in this picture than in this picture. But the higher resolution picture is also much more accurate. So as meteorologists, we're constantly playing this balance game between, do we want low resolution forecasts that are quick, that aren't expensive to make, and can kind of give us a picture, or do we want very, very fine-tuned, very accurate forecasts that take forever to make and are extremely expensive? Now, I mentioned a few minutes ago that we don't just do this at the surface, but instead we actually do it for the surface and for several key layers above the surface. And these key layers include the surface, which we just talked about, but then we also look at several key pressure levels above the surface. The first pressure level we look at is 850 millibars. And remember, this is the height where the pressure above us is 850 millibars. So we look at that pressure level. And at that pressure level, we look for things like moisture, temperature, and the low level jet. And these three things indicate advection. And if you remember, advection represents an air mass moving in or moving out. For the 850 millibar level, we're looking at more local advection, such as wind coming in off the ocean. And so that can give areas right near the coast much more moist air or much more moderate air, whereas areas inland are a lot hotter. On the other hand, continuing up, the 700 millibar level shows us large-scale advection. So now we're looking for advection along a frontal system or along some kind of synoptic scale weather pattern. Zooming out even further, at the 500 millibar level, we're looking for ridges and troughs in the jet stream, and also for the spin of the air. And this is what we call vorticity. And the spin of the air actually represents if air is able to rise or sink, if there's low pressure present, high pressure present. So the spin of the air is actually really valuable for us. Now, going into the ins and outs of how it behaves is a little beyond the scope of this class, but just know that we want to look at that level for the spin of the air. And then finally, at the 300 millibar level, now we're looking at just the large-scale jet stream itself. And then we look at each one of these levels, and we look at their current conditions, and then what is forecast for them in the future. And those forecasts are what are called progs. Basically, a prog is just a prognosis. It's a prediction. And a 24-hour prog simply represents a 24-hour prediction from now. A 24-hour prediction from now. And here's what they show us. So you can get a prog for the 850 millibar level. So that's at 850 millibars. So it's above the surface where the pressure is 850 millibars. And this shows us the position of surface lows, surface highs, and local advection. Then at 700 millibars, we're now looking for large-scale advection. 500 millibars, we're looking for troughs and ridges in the jet stream. So there's a trough right here, ridge right here, trough down here. Right over here, there's what's called a shortwave ridge. And so we're looking for these waves. And then if we want to look at the jet stream as a whole, we look at the 300 millibar level. And again, what's happening up here greatly influences what's happening down at the surface. Like right here, you see divergence. So right here, right along the interior west, these lines are pulling apart from each other. That's divergence. As you actually travel down towards the surface, what you'll actually begin to see is a low pressure system developing down there. And voila, the closer we get to the surface, the more we see a low pressure system. Now, with all of this said, I do want to mention that these equations are, again, just models. And so every model is different. So if you think about a real-life Boeing 747, and then you look at a few different models of Boeing 747s, every one of them is going to have a different size. One of them may have landing gear that retracts, the other one may not. Another one may not have landing gear at all. You may have to throw it. But each one has its own function, its own functionability, and the same is true for weather models. Every weather model has a different resolution, so how many grid boxes it represents the world as. It has its own set of equations, and every model has its own set of assumptions and approximations. And the most commonly used weather models that we use here in America are the North American model, also referred to as the NAM, the Global Forecasting System, or the GFS, and then the European model, the ECMWF. And then private industries actually have their own models. There's a very popular wind model called the USL model. It does a really good job of forecasting winds. And each one of these models has their own strengths and weaknesses. As I just mentioned, the USL model, really good with winds. But some of these models are really good with precipitation. Others are really good with temperature. Others are really good with forecasting advection, the movement of air. And every model has different strengths and different weaknesses. The final thing I'll mention is that these models are also useful if we actually use them in what are called ensembles. So think about this. Let's say you go to a doctor. Let's say you've been feeling sick and you go to a doctor and the doctor says, okay, you have the common cold. And you're not really satisfied with that. You feel like something deeper is going on. So you then go, okay, well, I'm not totally sure I agree with what he says. I'm going to go to another doctor, and the other doctor then says, okay, well, you just have a common cold. Here, take some Tylenol, go home, relax, you're going to be okay. And then let's say a third doctor then comes to you and also says, okay, well, yeah, you just have the common cold. Here's some Robitussin, you're going to be just fine. You would, after hearing 3 different doctors tell you that everything is okay, you just have a common cold, you're probably going to feel okay. Well, as meteorologists, we want second opinions, and we want third opinions, and we want fourth opinions. And the way that we do this is we don't just look at different models, but we'll actually take the same model and we'll slightly tweak the initial conditions. So we might make temperature a little bit higher, or we might make temperature a little bit lower, or we might double the dew point, or we might make the wind a little bit faster, or the wind a little bit weaker. We just make slight tweaks to it. And then we run the model and we look at how the results come out. And if all the results are in agreement, meaning they're all very similar, they all have very similar results, we say that that is a high confidence forecast. What that means is that, okay, well, even when I tweak the conditions a little bit, all the models are still saying the same thing. They're still saying that temperature is going to be this. They're all saying that dew point's going to be this. They all say the same thing. Awesome. That is a high confidence forecast. On the other hand, let's say you go to 3 different doctors. One of them says you have the common cold. Another doctor says you have hepatitis. And then a third doctor says that it's all in your mind and there's nothing wrong with you. How would you feel? Well, you wouldn't necessarily feel confident in what you have. So one doctor's telling you that you have the cold, another doctor's telling you you have the flu, you have another doctor telling you it's hepatitis, another doctor telling you that it's nothing. In that case, you have a low confidence in what you have. Well, weather models do this too, where every so often you'll run a model with different initial conditions, and the result it gives you is very different. compared to previous models, compared to the other models. In this case, you have what's called a low confidence forecast. In this case, you really aren't sure what's going to happen. Just like if 4 different doctors don't know what you have, or they're all telling you something different, in this case, 4 different models are telling you something different. Here's an example of a high confidence forecast versus a low confidence forecast. So this was Hurricane Sandy back in 2012. And Hurricane Sandy's initial position was right here. And we took all of our forecast models, ran them with all different initial conditions. And if you take a look, most of the forecast models actually stuck together in their projected path for it. They all had it turning to the east, kind of going in between the United States and Bermuda, and then they were all forecasting it to then make a sudden northwest turn and hit New York, New Jersey, and those areas actually were the most forecasted for it to hit. So this actually shows us that most forecast models were predicting that Hurricane Sandy was going to turn back and hit the United States. There were 2 forecast models that had it going out to sea. Every other forecast model had it making that turn. And if you take a look, most forecast models had it going over either New York or New Jersey. So we were then able to say, okay, this is very likely going to happen. All but 2 of the forecast models are saying this is going to happen. We need to warn these people. And this was actually a major victory for weather forecasting. On the other hand, here's another forecast, and this is for 850 millibar temperatures, and this was run by the ECMWF. And if you take a look, what you actually have are each one of these lines represents a different model run. All the model runs are very close to each other for initial, but then as you begin to get out, you have model runs that are completely different in what they're saying. You have one model run predicting an 850 millibar temperature of 25 degrees Celsius, while another model run is predicting an 850 millibar temperature of 2 degrees Celsius. Very, very, very different. And the ensemble mean was actually showing, so this is the mean of that ensemble. Basically, it was just canceling out very, very erroneously high values with very, very erroneously low values. This is what we call a low confidence forecast. Basically, all the model results are telling us very different things. And there's no real tightly packed pattern. Over here there was for the first day, day and a half, but the further out you go, the much more all over the place everything was. Now, with all of this said, the reality is that these models have their strengths and weaknesses. And it's up to us as humans to then determine what those strengths and weaknesses are and how to act accordingly. And we're going to talk about that in our next lecture. So until then, I'm Terrence Mullins. Thank you.